Right, the purpose of this video is to cover possible exam type questions, types of questions that you may come across while you are going through the section, while you're studying, questions that will help you to understand how we test this type of section. So the first question is question 1, and you would look onto the drive, you'll find it says photoelectric effect worked examples for video 3. You can print that and have it with you, or you can write out the questions, whatever you find is easier for you. So let's have a look at the first one. The first question says, define the following terms. So there's 3 terms you need to look at: photoelectric effect, threshold frequency, and work function. Alright, so let's look at the first one, the photoelectric effect. So with the photoelectric effect, you just have to give a brief definition as to what's going on. So we would say something like, the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that surface. So what we want to do is make sure that we answer these questions fully so that you can get the correct amount of marks. So a question like this is usually 2 to 3 marks. We're looking at things like electrons are ejected. We're looking at a light of suitable frequency. We're looking at those kinds of keywords. So I would suggest that for these questions, what would be better for you to do is pause the video, answer the questions, see if our answers are the same. If our answers are the same, then you can mark your work. If it's not the same, then add to your answer and see if where you're struggling or how you've not answered the question completely. Number 1.2 says threshold frequency. Right, with the threshold frequency, we know it's the minimum amount of frequency. It is the minimum frequency of light needed to emit electrons from a certain metal surface. Right. Number 1.3, check your answer. It wants the work function. We also know that deals with minimum energy. It's a bit different. It's the minimum energy needed for an electron to be emitted from the surface of a metal. Alright, so those are the 3 most common types of definitions they're going to ask you for. You need to be able to give them an answer, nicely, clearly, and in enough detail for you to get your marks. Also, it's these types of activities that we do, a good way of us to remember and memorize definitions, which remember must be word for word. Question 2. Calculate the energy of a photon of red light. So they want energy of a photon. Red light, it has a wavelength of 700 nanometers. So let's just write down the information. We want E at the end. Right? So I have 2 options. I've got E is equal to HF, or I've got E is equal to HC over lambda. Right. I want E, and they've given me wavelength. I don't have frequency, so I can't use that. I do have lambda, so I can use that. My frequency here, my wavelength though, my lambda value is sitting at 700 nanometers. That's not acceptable, so I've got to go 700 multiplied by 10 to the power of negative 9 meters. Alright, so I've got that sorted out. Now I can put it into my formula. I've got E is equal to hc over lambda. In terms of h, I know that's my one constant, my Planck's constant, and c I know is my speed of light. So I'll just get that from my formula sheet. So I've got 6.63 times 10 to the power of negative 34. All of that multiplied by, 3 times 10 to the power of 8 meters per second, speed of light, all over 700 times 10 to the power of negative 9. And I pop that into my calculator, and I should get an answer of 2.84 times 10 to the power of negative 19 joules. And that gives me my final answer. So formula, substitution, final answer, and that's how you sort that out. And the next question, it says calculate the energy of a photon, again energy of a photon of blue light that has a frequency of 5.40 times 10 to the power of 14. So again, they want E, energy of a photon. They've given you frequency at 5.40 times 10 to the power of 14 hertz. You've got two formulas, E is equal to HF, or you've got E is equal to HC over lambda. So you've got frequency, you've got Planck's constant, and you need your energy of a photon. So E is equal to HF. Your H is 6.63 times 10 to the power of negative 34 multiplied by 5.40 times 10 to the power of 14 hertz. And that's going to give you a total of, pop it into your calculator, you should get 3.58 times 10 to the power of negative 18 joules. Right, please make sure that when you're having a look here, you've got two decimal places. That's important. If you don't have two decimal places, you get penalized. So make sure that you sort that out. Don't just, so when you go onto your calculator and you set it up, make sure it's rounding off to two decimal places, not X, Y, and Z. All right, let's have a look at question 4. It says the work function of potassium is 3.66 times 10 to the power of negative 19 joules. We have to answer 5 questions in total. This is like an exam type question. So these are the types of questions that lead into each other. So as we work through these questions, you will see that they kind of run into each other. So we need to make sure that our calculations are correct so we can follow through. All right, so the first thing they want the threshold frequency. So you're looking at FO. And the formula that we can use for that is WO is equal to HFO. The next one is calculate the longest wavelength of light for which photoelectric emission will occur. So what you're looking for here is lambda. So you can either use E is equal to HC over lambda, or you can use C is equal to F times lambda. Question 4.3 says that this metal is irradiated with ultraviolet radiation with a wavelength of 220 nanometers. So I already know here I must do some sort of conversion. It says calculate the maximum kinetic energy. So they want EK max of the emitted electrons. And the next one says calculate the maximum speed of the emitted electrons. So they want V max at the end. So those are the things we're looking for. We're going to go through each question. I would recommend that you do each question by yourself, and then later on you can come and pause the video and then come and have a look at how you did. Alright, question 4.1. You need the threshold frequency. Work function is equal to H times FO. Our work function was given at 3.66 times 10 to the power of negative 19. Our H value we know as 6.63 times 10 to the power of negative 34. And we're looking for threshold frequency. Your threshold frequency is going to be equal to 3.66 times 10 to the power of negative 19, all divided by 6.63 times 10 to the power of negative 34, and you should get 5.52 times 10 to the power of 14 hertz at the end. There we go. Right, question 4.2. 4.2 says they want the longest wavelength. Right, so let's look at what information we have. So far, we have the work function, yes. We have the threshold frequency, we have H, we have C, and we need lambda. Okay. So if I look at my two formulas that I have available to me that have lambda, E is equal to HC over lambda, or I can use C is equal to F times lambda. Now if I'm looking at those two questions, I have H, I have C, I'm looking for lambda. I don't have energy of the photon. If I use the second formula, I have speed of light, I have the threshold frequency, and I'm looking for lambda, which means that's the only equation that's going to be relevant to us. So the first thing I'm going to write down is C is equal to threshold frequency multiplied by lambda, and I've got the speed of light at 3 times 10 to the power of 8 is equal to the threshold frequency, which I got from my previous question, which is 5.52 times 10 to the power of 14 lambda. Divide both sides by 5.52 times 10 to the power of 14, and my lambda value is 5.43 times 10 to the power of negative 7 meters. The nice thing about this section is we don't really need directions. Right, next question. Number 4.4. 4.4. Question 4.4 says, calculate, so we know we have ultraviolet radiation, so we have UV, and they've given us the lambda value at 220 nanometers. Right, so that's our information, and what they want from us is they want us to find EK max. So we just look at our formula for EK max, and our formula for EK max is E is equal to the work function plus EK max. Okay. Now we don't have energy of a photon. We don't have that. But energy of the photon, remember I said, is equal to HC over lambda. So that's one thing. I have H, I have C. They've given us the lambda value there, so I have that is equal to the work function. The work function they gave us is of the same metal. We've got the work function, yes, and we need to work out EK max. Right, so this would be the best formula for us to use. So I'll go ahead and I'll write E is equal to work function plus maximum kinetic energy, and then that's where you get your mark. Then I'll take it one step further and I'll say HC over lambda is equal to the work function plus EK max. Right, my H, what I can do now is I would manipulate my formula so that I can make EK max the subject of the formula. So it's going to be EK max is equal to the work function, the HC over lambda minus the work function. So all I did was I moved this over to that side. And this gives me a better formula for me to put all my information into. So it's easier to put it onto the calculator. So I've got 6.63 times 10 to the power of negative 34 multiplied by 3 times 10 to the power of 8 speed of light all over. Right, here's the thing. They gave you 220 nanometers. So that needs to be converted. So we're going to go 220 times 10 to the power of negative 9 meters. So substitute that in, 220 times 10 to the power of negative 9 minus 3.66 times 10 to the power of negative 19. Right, pop all of that into your calculator all at once, because getting a mark there, you're probably going to get a mark here, here, and here. And now you need a final answer, and you should get 5.38 times 10 to the power of negative 19 joules. And that is your EK max. Alright, so this was question 4.4. Question 4.5 says they want the maximum speed. So they want Vmax. Right. In order to get Vmax, so 4.5. In order to get Vmax, the only formula I can use is EK max. Right. My EK max, so I can say EK max, or maximum kinetic energy, is equal to half mv max squared. Right. I want Vmax. So let's look at what information I have. I have the EK max because it's going to come straight from that formula. But the thing that I also need now is I need, because it's mass of, because we're looking at electrons, we need to find the mass. Like I said, the mass of an electron is on your formula sheet. So your mass for this question is 9.11 times 10 to the power of negative 31 kilograms. So all I do is I substitute those values in. EK max was 5.38 times 10 to the power of negative 19, which is equal to a half multiplied by 9.11 times 10 to the power of negative 31 times V max squared. Alright, once I have that, all I need to do is get V max squared by itself. So divide both sides. I'm just going to do this in another color. Both sides get divided by a half of 9.11 times 10 to the power of negative 31. A half 9.11 times 10 to the power of negative 31. And then I'm going to have V squared, or V max squared, is equal to 1.81 times, 1.181 times 10 to the power of 12. And then both of those need to be square rooted. And I'm going to end up with V max is equal to 1.09 times 10 to the power of 6 meters per second in the direction of emission. Alright, and that's my final answer there. So marks over here, marks for substitution, and then marks for your final answer there. So please make sure that you are doing these little activities so that you can see where you're struggling. The next question says that ultraviolet radiation of frequency 1.65 times 10 to the power of 15 Hertz is shown onto a metal plate. The maximum kinetic energy of the ejected electrons is 2.8 times 10 to the power of negative 19. So the information you have here is of UV light, right? You've got frequency which is equal to 1.65 times 10 to the power of 15 Hertz, right? You've also got the EK, the maximum kinetic energy, EK max, at 2.8 times 10 to the power of negative 19 joules. So that's what information we have. Question 5.1. Calculate the energy of one photon. So energy of a photon, I have E is equal to HF, or E is equal to work function plus EK max. So if I look at the information I have of the two formulas, I'm looking for E in both. I have H and I have F. I don't have work function and I do have EK max. So I use the formula that is the best one, and that is E is equal to HF. My H is 6.63 times 10 to the power of negative 34. Please make sure you pause the video, you do it yourself, see if you get the right answer, then move forward. 1.65 times 10 to the power of 15. Pop that into your calculator and you're going to get 1.09 times 10 to the power of negative 18 joules. And that is your energy of one photon. All right, question 5.2. They want the work function of the metal. So the best formula for us to use is this formula here. So let's come down here. And we have E is equal to work function plus EK max. Alright, so I've got my EK max and I've got my energy of my photon. I just need the work function. So what I can do is, if I want to, I can manipulate this formula to make work function the subject, and I can say WO is equal to energy of the photon minus the maximum kinetic energy. So my energy of the photon was 1.09 times 10 to the power of negative 18 minus your EK max, which was 2.8 times 10 to the power of negative 19. And then that should give you the work function is 8.14 times 10 to the power of negative 19 joules. So there we go. That's how you would answer a question like this. So just be very careful, choose your formulas carefully, make judgments and assessments before you start. All right, so the next thing we're going to look at is we're going to be looking at energy of a photon, of which we can use any of these formulas, and in those cases we are given things like frequency, or we are given things like wavelength. Right? The other one is your speed of light, which a formula which relates to energy of a photon. The second thing they can ask you to do is work out the work function of a metal given the threshold frequency. So if I must realize now that frequency relates to the light. Threshold frequency is related to the minimum frequency needed. Okay. The next thing we're going to ask you to do, the work function of the metal. So let's just remember this. The work function of a metal corresponds to a maximum wavelength of light for which photoelectric emission occurs. And then the last thing we're going to look at is working out maximum kinetic energy, or they can ask you for the maximum speed or velocity of an ejected electron. Right? And then don't forget this E relates to that, this W relates to that, and EK max is half mv squared. And just because the next two questions that we're going to deal with are a little bit longer, a little bit more complicated. Let's have a look at our question here. It says, in the diagram alongside, electrons are released from a metal plate when a light of a certain frequency is shone on its surface. Alright, so what we've got here is we've got our diagram. The best thing to do with this diagram a lot of the time is to just quickly label things. So the first thing I know is they're always going to shine the light on the cathode, which is negative, and those electrons are going to move towards the anode, which is the positive side. This light that comes in has a frequency of some certain value. Alright, let's look at the first question. It says, so we understand that once that happens, once those electrons come through, I'm going to have my electrons moving through the circuit, and what I'm going to have here is an ammeter. So they can ask you to label it by putting in the symbol. So the symbol for an ammeter is capital letter A, or they can tell you that it's a galvanometer, and that's a capital letter G. Right. Name the phenomena described above. When I have light that shines onto a metal surface and I get this electrons being emitted, I have something called the photoelectric effect. Oops. Right. Then we have question 6.2. Question 6.2 says, the frequency of the incident light on the metal plate is 6.16 times 10 to the power 14 hertz. Electrons are released with a maximum kinetic energy of 5.6 times 10 to the power of negative 20 joules. Alright, so for 6.2, I'm just going to write down the information that we know. We know we have a frequency of 6.16 times 10 to the power of 14 hertz. And I know that we have an EK max of 5.6 times 10 to the power of negative 20 joules. Right, that's my two bits of information I know. And let's start with the first question. 6.2.1. It says they want the energy of the incident photons. Right, I've got E is equal to, oops, just write down all my formulas here. I've got E is equal to HF. I've got E is equal to HC over lambda. I need to pick one. So I've got frequency and I know H, so that's enough for me. So I can say E is equal to HF. The H we know is 6.63 times 10 to the power of negative 34, or multiplied by a frequency at 6.16 times 10 to the power of 14. Again, try and do these by yourself so you can get some independence. 4.08 times 10 to the power of negative 19 joules. Alright, there's 6.2.1 done. Right, the next thing they want is they need the threshold frequency. Right. If they need the threshold frequency, the formula that we have for threshold frequency is WO is equal to HFO. Right? That's my formula that I can use. Okay. In this formula, I have H. But I don't have, and I'm looking for a threshold frequency. The problem is I don't have my work function. Now, this is one of the formulas for work function. The other formula for work function is E is equal to work function minus EK max. Right, so that's your other formula that you have available to you. Now, of this formula that I have, I was given the EK max from here in the question, so I've got that. And in 6.2.1, I found the energy of one photon. So I can use that information to find my work function so that I can sub it back in. All right, so let's have a look at how this is going to play out. 6.2.2. Right, the first thing you write down is E is equal to WO plus EK max. And you'll manipulate your formula only to make life easier for you. And you'll say WO is equal to E minus EK max. Right, then pop in all the information that we do know. So I know that the energy of the photon was 4.08 times 10 to the power of negative 19 minus the EK max they gave us at 5.6 times 10 to the power of negative 20 joules. That's going to give me a work function value of 3.52 times 10 to the power of negative 19 joules. Great. I'm going to take that information and I'm going to go WO is equal to HFO, where WO is 3.52 times 10 to the power of negative 19 is equal to 6.63 times 10 to the power negative 34 FO. Divide both sides by 6.63 times 10 to the power of negative 34. And then I'm going to get FO is equal to 5.31 times 10 to the power of 14 hertz. And now I've got my threshold frequency. Right, so this becomes important to us now. The best thing to do is to write down all the info that we have found and that we know. So I know that the frequency of the light was 6.16 times 10 to the power of 14. I know that information. I know that my work function is equal to 3.52 times 10 to the power of negative 19. I've got EK max, which is 5.6 times 10 to the power of negative 20. I've got my threshold frequency at 5.31 times 10 to the power of 14. That's hertz, joules, hertz. Right, and then I know H, I know C, stuff like that. Right, that's the information I have. So I need to use this information for the questions that come next. Let's have a look here at the next half. Right, it says the brightness of the incident light is now increased. Right? What effect will this change have on the following? You can write increase, you can write decrease, you can write remain the same. And let's have a look. They want you to check. If I'm increasing the brightness, then essentially I'm increasing the intensity. Right? And if I increase the intensity, they want to see how does it affect the reading on the ammeter. So what does it do to the current? Does it increase it? Does it decrease it? Does it keep it the same? And then they want to know what happens to the kinetic energy of the released photoelectrons. Does it increase, decrease, remain the same? And now they want an explanation. These questions go for 3 marks, sometimes 4 marks. You need to be able to answer them correctly. So let's have a look here. If I do 6.3.1, I know that if I have a high intensity, that means more photons, right? And more photons means that, remember, each photon will end up giving me 1 electron ejected. Now, if I increase the number of photons, I'm going to increase the number of electrons ejected. Right, so we need to use that thinking process. So if I've got, so let's write this down. By increasing the light, more photons are arriving at the metal surface per second. Right, that's the first thing. The second thing is, if that happens, more electrons are ejected per second. And that means more electrons will pass through the ammeter. Right? Or I can say, better to say, more charge is arriving at the anode per unit time. Please make sure you add that little bit. Now, if I have all of this as more, that means, therefore, the answer is increase. Right. So sometimes I find it's better to write your reasoning as to how you got to your answer than to write down increase and then try and explain why you're saying increase. So either way, make sure that when you're writing it down, it makes sense to you. 6.3.2. Right, now they're talking about kinetic energy. Now, if I increase that intensity of the light, I'm getting more photons. But does it really affect the speed? So the only thing that affects the speed or will increase the EK max is if we look at frequency. So first of all, you can mention the frequency of the incident light has not changed. Right? Now, if that has not changed, it means, therefore, the energy of the incident photon has also not changed. Now, if the frequency has not changed and the energy has not changed, it means that the kinetic energy has not changed. The kinetic energy has not changed. None of it's changed. You just made the bulb a brighter bulb. So what's going to happen, therefore, your answer for the 6.3.2, they want to know how does it affect the kinetic energy of the released photoelectrons. Is it increase, decrease, or remain the same? Because nothing has changed, we can just say remains the same. Right. Right, so far we know that the rate at which photoelectrons are emitted from a photoemissive surface is, number one, it's determined by measuring electric current. And the second thing we know, it is directly proportional to the intensity of the incident light. When frequency is constant. Alright, so that's the two things that we know about the rate at which photoelectrons are emitted from a photoemissive surface is a metal. Right? The next thing that we look at, or that we understand here, is we're going to be looking at a little bit about the maximum kinetic energy. Right. Of the maximum kinetic energy here, we know that it only increases linearly with the frequency of the incident light, and it must be above the threshold frequency. Right? Another thing about the EK, it is independent of the intensity of the incident light. So now we know things about the maximum EK and we know about the rate. Now that leads us to graph questions. So this over here is a graph showing, and you should get this into your books please, the maximum kinetic energy versus the frequency of metals. So when we're looking at this kind of the graph, the first thing that we need to notice is that all the curves or gradients are linear, right? So they're linear with the slope, right? That means we can use y is equal to mx plus c. We're going to use our linear function in order to calculate the slope. On these kind of graphs, the slope is equal to Planck's constant. Let's put that there. Which is h is equal to 6.63 times 10 to the power of negative 34 joule seconds. Right? So that's the one thing that you need to know. You need to know what your slope represents on a kinetic energy versus frequency graph. The second thing that we look at is we look at the intercept. Right? On the energy axis. Right? The x-intercept is equal to the threshold frequency of the material. So over here we can have a look. I'll just highlight it for you. Over here, can you see? Wherever it intercepts the x-axis, that is going to be your threshold frequency, which is your FO. Using graphs to observe the photoelectric effect, or using graphs to represent the photoelectric effect, is something that's quite important, because you're going to be given these graphs and we're going to ask you for information. So what we're looking at here is that you must understand that the EK value is plotted on the y-axis. That means you can take those values and put them directly into your equations. So I can take the value straight from the graph on the y-axis, and that forms part of my formula. Your x-axis is your frequency, and that's over here, frequency, and that value can go straight into your formula as well. Your x-intercept, I'm just going to do it in a brighter color. Your x-intercept over there is also on your graph, and you can add that to your equation. Your h values obviously come from the slope itself. So when we have an energy versus kinetic energy versus frequency graph, we must note that when a light is shone onto a metal surface and we get this graph drawn up, there's two parts that you need to understand. If the frequency is less than the threshold frequency, you're not going to get any emission. And that's always going to be on the left-hand side of your gradient. So what I'm looking at then is over here. Oops. I'm looking at this zone here. You're not getting any emission here, right? If it's on the right-hand side, it means that the frequency is greater than the threshold frequency, and you're going to get emission. And when you get emission, you're going to get a gradient here, right? So that's what we need to look at. Don't forget, the slope is the gradient of the graph, which is the m of your graph. There we go, is Planck's constant h. And that we know that the x-intercept there, oops, let's just do it like this. It's Planck's constant, and that your x-intercept, and we'll use the same rules. So if I want the x-intercept, then I'm going to just say y is equal to 0, and then go ahead and work out my x-intercept at the coordinate, and then that would be your xy coordinate for the x-intercept. Now let's have a look at a question that deals with all of this stuff. Go back here. When I'm looking at EK max, it will increase linearly. Let's use another pen. It will increase linearly if the frequency is above the threshold frequency. However, EK max is independent of the intensity of incident light. During an investigation, light of different frequencies is shone onto the metal cathode, and we know cathode is negative, of a photocell. The maximum kinetic energy of the emitted photoelectrons is measured. The graph below shows the result obtained. Alright, so we've got our graph over here, and now we have to answer the questions that they've given us. We can see there is an x-intercept on our graph, so we already assume that they're going to ask us to work out some of these things. Alright, the first question says, for this investigation, write down the dependent variable. So remember, the dependent variable is always on the y-axis, and we're looking at maximum kinetic energy. Please don't just write kinetic energy. Maximum kinetic energy is the one, and that is measured in joules. The second one says, what is the independent variable? The independent variable is always on the x-axis, and that is the frequency. Oops. Right, and then the last one, they're asking you, what is the control? So in this whole situation, or in this experiment, you've got different frequencies of light. And throughout this means that we're always going to be changing these. Right? We'll make changes to these. By making changes to these, we're going to get EK max. and that's going to be what we measure. Right? When we talk about a control variable, we're meaning that it is something, and we've discussed this, something that doesn't change right through, it's fixed. So in this instant, the one thing that we're not changing each time, remember, it says here, different frequencies are shown onto a metal cathode, that of a photocell, which means that's the one thing that doesn't change. So your control variable here, you can write down the metal, rather write down, oops, the type of metal cathode. If you wrote type of metal, that could be also considered as correct. So there, dependent variable, independent variable, control variable. Let's have a look at the question further. I have question 7.2 states, define the term threshold frequency. So we know now, by this point, the threshold frequency is the minimum, frequency of light needed to emit electrons from a certain metal surface. Right, nice and basic. 2 more questions, just a plain old definition. Right, question 7.3. It says use the graph to obtain the threshold frequency of the metal used in the cathode in the photocell. So we understand now that the threshold frequency is the x-intercept, right? This corresponds to an electron which is set free from the metal surface with 0 kinetic energy. So that's another thing. This corresponds to an electron which is set free from the metal surface with a 0 kinetic energy. Because remember, threshold frequency, there is no kinetic energy. It's the minimum amount of frequency of light. Alright, so let's just have a look here how that works out. So if I go to my graph, and you got to get really detailed, I'm just going to zoom into it quite a bit. Look at my graph here. I must understand what units they're using. So to get from 0 to 5, let's just have a look at what intervals they used. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they got to 5. So that means they're moving in 2s. And then there's this one. 2, 2. 2. Right, so we're looking here. So to get to 10, so it's 1, 2, 3, 4, 5, 6 times 10 to the power of 14, 7 times 10 to the power of 14, 8 times 10 to the power of 14, 9 times 10 to the power of 14. So our x-intercept, or rather our threshold frequency, so the x-intercept is at 9 times 10 to the power of 14 and 0. So therefore your work function is equal to 9 times 10 to the power of 14 hertz. And there's your answer for question 7.3. Right, so just make sure that when you get into the graph, you get quite detailed so that you can get the exact value. Right, question 7.4. It says you calculate the maximum kinetic energy at E1 shown on the graph. So E1, and at E1 we're looking at the EK max. Right. So now you go back to your graph, and I want to go to E1. So go to E1 and see where that coordinate is, and that coordinate is all the way over there. So what I want to do is, I'll just check it along the x-axis so I can get some values here. I've got it here. Let's change my point so we can see better. We've got it going down. Oops. Over there. And across this way. We've got it look at something like, sorry, just getting this lined up. And that's where we're looking at, on that line. Alright, so now we need to do a calculation. What they want from us is they want this value over here, E1. Alright, so basically we are looking for EK max. This line here, remember what I said? 11, 12, 13, 14 times 10 to the power of 14 hertz. That is the frequency. Okay, so that's where E1 lines up with. Let's go back here. Alright, so for this whole setup, for this question, I know that my frequency is equal to 14 times 10 to the power of 14 hertz. I know my threshold frequency is 9 times 10 to the power of 14 hertz. I know C, I know H. I'm looking for EK max. Right? And that's about it. So the first thing I want to do is I want to write down my formula. So the formula I've got here is energy of a photon is equal to the work function plus EK max. Right. Do I have I'm looking for EK max, so I know I'm going to manipulate my formula at some point. So that's fine. My problem is I don't have the work function. But work function itself, over there, is equal to HF. I know that much. I also know I also know that E is equal to HF or HC over lambda. Now I don't have lambda, so I'm not even going to bother with that. Or looking at that. Okay, so I know I can't use that. I know I need HF for E. I know I need HFO for work function, and I'm looking for EK max. And I've got H and C and whatever other information I need. Right, so the next step is to start with my calculation. So I've got here for E, I've got HF is equal to HFO plus EK max. Right, the first thing I need to do is sort my formula out so that it looks a little bit better for me to work with. So I'm going to say EK max is equal to HF minus HFO. And then I'm just going to put all the information in. I've got 6.63 times 10 to the power of negative 34 multiplied by my frequency of 14 times 10 to the power of 14 minus 6.63 times 10 to the power of negative 34. All of that multiplied by 9 times 10 to the power of 14. And I just put that into my calculator, and I get for EK max, I'm getting 3.32 times 10 to the power of negative 19 joules. And that's how I get there. So it's not just, I don't have work function, so I can't use the formula. Work function has its own formula, you got to bring that in. I don't have energy of a photon, but I have other information that can help. So remember, always write down your equation. Try and do some sort of expansion into its individual parts. Number 3, substitute. And then number 4, you need an answer with the SI unit. So have some sort of system that you use to get through questions like this. All right, the last question, question 7.5. Let's have a look at what it says. How would the maximum kinetic energy calculated in question 7.4 above be affected if a light of higher intensity is used? Write down only increase, decrease, and same. This remains the same. So remember what I said before. So that means if I look at my EK max here at 3.32 times 10 to the power of negative 19, how will it be affected if we use a higher intensity? It will not be affected, as EK is independent of light intensity or even brightness. It's a different word that they could bring up. Therefore, it must remain the same. And that's your final question. That's question 1 to question 7. The next thing you're going to do is you're going to watch video 4, and that's the emission and absorption spectrum. It's a little bit more complicated, but I will attach a note to it, and on the note will be your diagrams. It would be recommended that you print those in color and then stick them in your book as you see them in the video, so that you have a good visual representation of what we mean by absorption spectra and then emission spectra.